Thank you very much. So the main goal of this course is to give some background material, some basic p-adic Hodge theory, and provide connections between p-adic Hodge theory and the content of our mini courses. So let me start with some general notation. So let K be a field. We fix a separable closure K bar over K. And denote by GK its Gala group, so the absolute Gala group of K. And let me start with l-adic representation. So for a moment, L is a fixed prime. And an l-adic representation of GK is by definition a finite dimensional QL vector space V equipped with a continuous linear action of a group GK, which can be written as a continuous homomorphism from GK to the group of automorphisms of V, which is isomorphic once we fix a basis of V to GLD of QL, where D is the dimension of V. So from the compactness of GK, so this map is continuous by definition. And this explains why the choice of L is important, because GK is equipped with Krull topology, so it should be continuous, continuous map, and it defines heavily on the choice of L. And the first remark, which comes from the compactness of GK, is that we can always choose a ZL lattice, say T in V, which is stable under the action of GK. And therefore, if we choose a basis appropriately, we can always consider morphism from GK to GLD ZL. So why these objects are interesting is because, so by many reasons. First of all, they appear naturally in algebraic geometry as Tate modulus of abelian varieties, or more generally as l-adic et al. Cohomology of varieties over fields. And maybe more abstractly, if our aim is to study the structure of the Gala group, so the direct approach seems to be too much difficult. So many results are known for special fields K about the structure of GK, but if the field is interesting, so the structure is absolutely Galois group is too much complicated. So for example, if you consider local fields, so the structure of abstract structure of its absolute Galois group is known for a long time, but this description says very few things about arithmetic properties of a Galois group. For example, we have very partial information about the ramification filtration of GK. And the approach via l-adic representations in some sense linearize the problem. So instead to consider some complicated group, we consider the category of its representations, which have some linear structure. So this is a linearization, some sense linearization of a problem. Let denote by rep GK the category of QL representations, l-adic representations of GK. And this is a abelian category. This is a tensor category. And the tensor product satisfies many properties, which is easy to write down, but there are so many properties which I cannot overview all of them, but they can be summarized in a very abstract way, saying this is a Tanakian neutral category. Okay, and we have the category of integral l-adic representations, given by free ZL modulus. Equipped with Galois action, and we have a natural functor from this category to that one, which is a tensor product, so the extension of scalars from ZP to QL. And this remark provides remarks, just says that this function is essentially surjective. So let's now consider the case of local fields. So from now, K is a local field. So we have two cases. So we have the characteristic, non-zero characteristic case. It denotes the characteristic by P. And in this case, K is isomorphic to the field of Arran series with coefficients in a finite field. And the zero characteristic case, where K is a finite extension of a p-adic field QP. So in both cases, we have the following tower of extensions. So if we want to approach to the algebraic closure or separable closure of K, we can start by taking its maximal unramified extension. The Galois group with this extension is easy to describe. The procyclic group generated by Frobenius. Next, we can take the maximal tamely ramified extension. And tamely ramified extension is generated over the maximal ramified extension by adjoining all roots of so let's fix a uniformizer of P of k in both cases. And we adjoin roots of order prime to P of the uniformizer. Okay. So this Gala group is isomorphic to the direct sum, sorry, direct product over all prime Q different from P over copies of ZQ. Here we go to K bar, and the Gala group of K bar over tamely ramified, the maximal tamely ramified extension is so-called wild ramification group. This is pro-P group. Sorry? Yes, yeah. 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 So this is the inertia group, and here we have the Volga group. Okay. So let's now consider the case of different characteristics, where L is different from the residue characteristic of K. So in this case, let's consider the following function Tk defined on the inertia, the whole inertia subgroup of K with values in L. So it is given by the following formula. So if an element of the inertia group acts on Lmth roots of a uniformizer, so this can be written in the following form. Here we fix some Lmth root of unity. And this gives a well-defined homomorphism Tk. Yes, thank you. And sure that these factors for the wild ramification when we have the following theorem, Grothendieck monodromy theorem. It says that in this context, if V is an l-adic representation of GK, where L is different from P, then there exists an open subgroup U of the wall inertia subgroup, and a nilpotent operator N on V such that on U the l-adic representation can be written as the exponent of kg n. So the idea of a proof is very simple, because if L is different from P, the restriction of representation on the inertia, on the wild inertia group factors through a finite quotient, because L is different from P, and this map should be continuous, and p-adic topology is not compatible with l-adic topology. So choosing some open subgroup U of the inertia group, we can trivialize the action of wild ramification on the p-adic and l-adic representation. So we need only to consider the action of a maximal tame extension. And in the Gala group, the Gala group of a tame extension is easy to describe. And we have first of all the lift of Frobenius operator, a subgroup. So I will write it down. We have a following exact sequence, tautological exact sequence. The Gala group, the black, this one. Oh, thank you. The Gala group of a tame extension over unramified extension. The Gala group of tame ramified extension over K, and the Gala group of maximal unramified extension, which is generated by the Frobenius. Okay, we can lift this Frobenius arbitrary here, so I denote again this lift by the same character. And here we have so take some element G. And when we can write the relation between a G and the lift of Frobenius, which says that this composition is equal to the composition of a Frobenius, G at Tk of G Frobenius. And if we define the operator n by this formula, so we have the following relation between Frobenius and the monodromy. Sorry, I said something stupid. G at Q, where Q is the order of a residue field. And from the definition of n, we have the following relation between the Frobenius and monodromy. And this implies in particular that n is nilpotent. So one of important problems of the p-adic Hodge theory was to find an analog of this theorem when L is equal to P. So now we switch to this situation. From now we'll talk about p-adic representations and assume that L is equal to P. It's defined by this formula. When U is sufficiently small, you can take the logarithm of G and define the n by this formula. And the problem is to find, to show that n is nilpotent, but this follows from this relation. Because if you look at the eigenvalues of n, you see that they are all zero because of this relation. Okay, now let's assume that L is equal to P. And first consider the case of fields of characteristic P. So here it is not so much important to assume that K is a local field. So the same theory will work for all fields of characteristic P. So let's first pass to radical closure of K. In order to get a perfect field. So the Gala group of K is, and F, the Gala groups are isomorphic. So we can instead K to study p-adic representations over F. Let's denote by OE. So this is some standard notation of the theory. The ring of Witt vectors with coefficients in F. So for us, it is only important to know this is a complete discrete evaluation ring. With maximal ideal generated by P and residue field F. And we will denote by E the field of fractions of this ring, so it is enough, it is sufficient to invert P. Let's also consider with vectors with coefficients in algebraic closure of F. And I will denote it by or E unramified hat. And by E unramified hat, the field of fractions of this ring. And just from the construction from standard properties of with vectors follows that this is a completion of a maximal unramified extension of E, and this is its ring of integers. So we have two structures on these objects. So first, we have the action, continuous action of the Gala group of F. And the invariants are exactly elements of E. And also we have a Frobenius operator on F bar, which induces Frobenius on with vectors. So we have two structures. So now we define the notion of a phi module and of a tal phi module, which is quite important, at least for this course. It is important for the whole theory. So a phi module over OE, respectively over E, is a finitely generated free OE module, respectively E vector space of finite dimension, equipped with a semilinear operator so let's denote this module by D. Semilinear operator D. And we will say that phi module is étal. So maybe here I will immediately assume that phi is surjective. Even isomorphism. No, not isomorphism. It is not good. No, not sorry. Okay, no. Let's for a moment let's keep this definition. So phi module D is étal if and only if so its matrix is invertible over OE, respectively in E, or equivalently, if we consider the map from D tensor or E with respect to the map phi, where this notation says that we consider or E as a module over itself via this map. And consider the map from this tensor product to D given by the following formula. Is an isomorphism. So later we will relate this with the theory of slopes, but for to state the next theorem, this description sufficient. And for E, this is the same, definition is the same, yeah. Yes. Yeah. So we have a category of all phi modulus, say over OE, and the subcategory of étal phi modulus. And for us, it is important that this category is abelian tensor category. So it says an easy statement. So maybe I will comment this definition, the definition of étalness, which will also explain the proof of the next theorem. So remark. So assume that D is an étal module over OE, and consider its reduction mod P. So this is a phi module so if we quotient with the ring of fit vectors by P, we get F. So this is a phi module over the vector space F. So let's take a basis E1, E2, ED of M. And let's write the action of phi in this basis. The coefficients are in F. Then we can consider the following algebra over F. So we take the quotient of this polynomial ring by the ideal generated by all the family of elements for all I. And just from the etalness of phi, it follows that this is an étal F algebra. And also that if we are interested in the homomorphisms over F from M to the algebraic closure of F, we consider only homomorphisms fixed by the Frobenius. Then this is exactly the set of homomorphisms of this algebra to F bar. And in particular, because A is étal, we see that this object is a Fp vector space of dimension d equal to the rank of a phi module. So now we can state the classification theorem, giving some description of p-adic representations in the characteristic pKs. In Fontaine's paper in Grothendieck Festschrift, but I think that maybe not in this form. It was known, it had been known before, but so I don't know. Consider the following functors from, say, functor D from the category of p-adic representations, so integral p-adic representations of GK. Sorry? Yeah. But you can compute the determinant, so that's also, this is a criterion of etalness in terms of differential forms. So it's, so we consider the functor D to the category of étal phi modulus over OE. It is not automatic, but it will be. It is a part of a proof to show that this function is indeed gives an étal module. So we start with a p-adic representation, say T, or okay, V. We take its tensor product over ZP with or E unramified hat, and we take the Galois invariance of the tensor product. So this is an OE module, because the OE is invariant, is stable under the action, is fixed by GK. And the functor V or E from the category of Étale modulus to the category of p-adic representations. Again, one should check that we get a p-adic representation. Given by the following recipe. We start with a Étale module D. We take its tensor product over OE with OE unramified. And we take the invariance under the action of a Frobenius. So automatically, we see that this is a ZP module. Point is that it has the same dimension of a rank of D. More explicitly, so if we consider these two functors, then D or E and V or E are equivalences of categories quasi-inverse to each other. So first of all, one can reduce this theorem to the same statement mod P. So we can consider representations over the finite field or FP. When our construction mod P gives the following, so when we go from p-adic representations to phi modulus, we take the tensor product of V over Fp with the algebraic closure of F. We take Galois invariance, and in fact, we can show that if we take Galois invariance and next, so this is a F vector space, and next we extend scalars to F bar, when it is canonically isomorphic to V tensor F bar over Fp. And this is this follows from Hilbert-Nancy theorem, which says that H1 of GF with coefficients in GLD F bar is trivial. So we have a vector space with a semilinear action of a Gala group. We can always find a invariant basis. So this explains why this map is an isomorphism. So this is our D mod P, and we recover V. So this isomorphism implies that the composition of D and V in this order is quasi-isomorphic to the identity functor. Conversely, if we start with a phi module, if M is a phi module, again, consider the situation mod P, so this is a phi module over F. We should check that if we take the tensor product of M with F bar over F, take invariance on the Frobenius, then after extending scalars to F bar, we recover M tensor F bar over F. And we should show, sorry? Yeah, thank you. So the key point is to show that this vector space of invariance is of dimension equal to the rank of M. And this follows from this property. So here we consider Homs, but we can pass to dual object, use duality, and to prove that this is a vector space of a good dimension. So this vector spaces are of the same dimension, and we only need to show that this map is injective. And the injectivity follows from a standard argument known as Artin's trick. So morally, we assume that the kernel is non-zero, and in the kernel we choose an element of smallest length, and we show that it can be reduced to a smaller element, and this gives a contradiction. So, okay, now we pass to the main. So from now, K is a complete discrete valuation field. Of characteristic 0. With perfect residue field. Say small k of characteristic P. And we consider p-adic representations. So consider the category of p-adic representations of GK. In principle, no. No. But it should be perfect. Yeah, it's important. Yeah. So this is a long story and maybe initiated by Tate in the 60s. And next, in the 70s, 80s, and 90s, Fontaine developed a general approach how to classify these representations by using different ideas, so using several different approaches, and studied the links between these different approaches, which culminated at the end of the 90s with a proof of main conjectures of Fontaine theory. But for a moment, let's just discuss how we can describe this category. Yes, sure. So they take a discrete relation field with a residue field, a field of functions of one variable. Yes, yeah. So roughly speaking, you extract some non-perfect field in the field of Witt vectors over F, for example. Okay, so let's consider the context of a previous lecture. Take a simple, infinite, totally ramified extension of K. For example, it's a p-adic cycloatomic extension. So we have a whole Galois group, and this group HK here, and a simple extension. Let's denote by gamma its Galois group, which in any case is a subgroup of ZP star. So, then by Fontaine-Witten-Berger theorem, or in a more modern language, using the theory of perfectoids and the last theorem of previous lecture, we can say that if we can consider the tilt of K infinity, completed K infinity. Here we have the tilt of, let's denote by C, the completion of an algebraic closure of K. We can take the tilt of C, which is algebraically closed. So here we have the maximal algebraic extension, algebraic closure of K hat tilt. And this Galois group is isomorphic to HK. So if we have a p-adic representation of, sorry? Here? This is the algebraic closure of this field, yeah. Yeah. Sorry, again? I don't understand. This one and that one? These two things? No. So we take the completion of K infinity, yeah? We take the completion of K infinity. This is a perfectoid space. We take the tilt of it.
That's missing all the K's go up. And of that, up. You're missing the subscript up.
Here?
Yeah, that's K infinity.
Ah, sorry. That's it's so stupid that. Yeah. Okay, yeah. Here, yeah, sure, yeah. Sure, yeah. Because we have this field of characteristic P, which is a tilt of cyclotomic extension, yeah. And here we take the algebraic closure of this field of characteristic P, which lives inside the tilt of C. And it is dense here, but. Well, this is a tilt construction applied. So we are exactly in the context of a previous lecture. So we have two perfectoids, K infinity completed, and C. Yeah? So we take the corresponding fields of characteristic P. Yeah? So this is a complete algebraic closure field. So therefore, the algebraic closure of a tilt of K infinity lives inside. Yeah? But it is not the same thing, because this field is not complete and this one is complete. But this is a completion of this one. Yeah. Yeah. Okay. So now if we have a p-adic representation of GK, say V, so the restriction of this representation on HK can be viewed as a representation of local field of characteristic P of K infinity, tilt of K infinity. Or, because we can decomplete the situation, okay, so it doesn't matter, okay. Of a field, of the Gala group of this field, of the Gala group, of a field of characteristic P. So, yeah, I finish in 2 minutes, maybe in 1. So, there is therefore the restriction of rho on HK can be classified using the previous theorem, because we can view it as a representation of a Gala group of a field of characteristic P. But we lose the action of gamma. So we should recover it some way. So this gives rise to the theory of étale phi modulus with an extra action of gamma. So this is a Fontaine's theory, phi gamma modulus. So this is an important theory, but in the next lectures I will mainly describe the more classical, the first approach of Fontaine, using p-adic rings Bicris and Bideram. And from this point of view, it can be seen as the following idea. So we want to encode the action of gamma in another structures. So we should consider phi modulus, étale phi modulus, in some sense, but replace gamma by some structures like, for example, filtration. And yeah, I will explain in more detail tomorrow. So thank you, I'm sorry. Yeah?
Will you consider representation over finite attention of QP?
Oh, so more or less this is the same, so parallel theory, yeah. We can take extensions, yeah. Yeah. But for simplicity, so it can be done, but for simplicity I consider only these coefficients, yeah.
So here, in this, where there are lots of questions about the second field and the top field, is it some commuting, that completion commutes with tilting or something like that?
Yeah, yeah, yeah. But in some sense, for formally, we apply tilt to complete objects. Yeah. Yeah.
So you tilt and you complete. That's the same as completing and tilting. No?
No.
Tilted uncompleted thing.
So we apply tilt to complete fields. Yeah.
Right. Yeah. No, but then you said that the top field, so that's still confusing me. So the top field, you said to go from the middle field to the top field, you complete.
Yes.
So what do you mean by that?
Oh, because... So
it is still...
this is, yeah. This
it's
is
not a perfectoid, so the one in the middle is not perfectoid.
No.
Okay, so you complete to get
yeah,
a perfectoid.
Yeah.
Let's wait for lunch. It's time.